In this video, we're going to look at graphing rational functions. We'll take kind of two views on it. The first one's going to be transformations, and these I won't go through them all again. They're the same transformations that we've seen 4 times, I think, already in the course. We'll see them 2 more after this. And then in the second part of the video, we'll look at more like what we did in the last section with the vertical and horizontal asymptotes and the x-y intercepts. And then we'll use that information and a graph to write the equation of a rational function that's a bit more complicated than the ones that we'll be graphing in this first part. So our two parent functions are 1 over x and 1 over x squared. Unfortunately, there are no good graphing questions available for the 1 over x squared ones. The few that there were seemed really buggy, so I didn't want to put them on the homework. We will see this idea towards the end of the section when we're writing equations from graphs. We'll see this behavior where the graph goes off in the same direction, and that's because it's an even power. When I put in a -1 there, -1 squared becomes 1, and so both branches of the graph go the same direction. When it's an odd power, we get like 1 over x. That's where we get one side goes to infinity and the other side goes to -infinity. Since we've looked at that last section now, we can talk a little bit more about vertical and horizontal asymptotes as it relates to 1 over x. Remember from the last section that if we look for zeros in the denominator, whatever would make the denominator 0 is undefined in the function, and it produces a vertical asymptote. At least for our purposes, there's one other case out there, but we're not looking at that this quarter. So this one's going to produce a vertical asymptote at 0, and so that's what we're seeing kind of right there. Thicken that up just a hair. There we go. That's our vertical asymptote at x. That's going to do this whole time equals 0. The other thing we had was horizontal asymptotes, and remember when the degree of the numerator is smaller than the degree of the denominator, or small over big, for that we got a vertical asymptote or a horizontal asymptote at y equals 0, and that is what we're seeing right there. And so that's our parent function. The asymptotes intersect at the origin, and then you can see if we put a 1 in for x, 1 divided by 1 would be 1, and we get that. If we put a 2 in for x, we would get 1/2, which we're seeing there. If we put 1/2 in, we get 2. And then the same thing on the other side, but negative. So that's where our parent function comes from. When we go to graph these on the computer, and let me just pull this over, there's a video here in the header with me graphing a bunch of these on the computer, so if you want to see a lot of them, go ahead and watch that. To graph these, there's going to be this graphing tool here, which I think is already automatically selected since it's the only one. And then the first dot you put sets the x and the y intercept, or the x and the y asymptotes. The second dot defines the function. So if there is no stretch on this, all you have to do to get this graph is put a dot right there, and it fills in the rest of the graph for you. For most of this video, I'm going to graph with my hand, because when you go to do this question on an exam, it's going to be on paper and pencil, and it's not going to draw it for you. So I want to make sure I show you how to do that as well. In terms of the homework, that's what that's going to look like. The other thing that I wanted to show you on the computer, because it draws it so much better than I do, is what a stretch would look like. And this is actually the first 2 questions that I was going to go through on the homework. I'm just showing them on here. So this would still have there's no left-right shift or up-down shift, so we're still with a horizontal asymptote at y equals 0 and a vertical at x equals 0. With this being a 5, so it used to be when I put in 1 with 1 over x, it would come out 1 and I would get that. Now when I put in 1, what I'm going to get is 5. And so that's that vertical stretch, but hopefully you can see it a little bit better with their graph, because it draws it cleaner than I'm going to be able to. That instead of getting out 1, I'm getting out 5 times as much. When I go to graph this on paper, I need to kind of get the other side set. So notice if I put in 5 divided by 5 would be 1, and that's that point right there. So if I had a stretch of 5, I'm essentially going to count up 5 boxes and put a dot, and I'm going to count over 5 boxes. Those are both on 1, and put a dot, and then that's going to help me kind of get this graphed. And once you have one side, you can use symmetry to graph the other side. So there's a little bit on graphing on the computer. Let me get that out of there now. And then let me show some more with graphing these on paper. So those are essentially the two that I just did. For graphing this on paper, you don't have to draw the asymptotes, but that can actually kind of be helpful, especially on the later graphs with some shifts. So I may not do this every time, especially if it's still at the origin. But there's our asymptotes. And then we know that it goes when x is 1, y is 1. So that kind of fixes that corner. And then in terms of an exam, for me, what I'm drawing right here gets it done. So that is all good. This one where it's 4, so that's the one where I was saying if I was drawing this on an exam, and you do want to get the stretch right? Like it doesn't have to be pretty, but it needs to be in the right place with the right stretch. So for this one, instead of 1, 1, it's going to go through 1, 4. And instead of 1, 1 going this way, it's going to go through 4, 1. And so that's what I was saying, is you can just use that to get those in the right places. And after you graph a bunch of them on the computer, that will hopefully get easier. So let's see. So for this next one, this has a +5, and that would be on the inside. Right there is what it will look like when it's on the outside. So a +5 on the inside is going to shift us left 5. So I'm going to go ahead and draw in the vertical asymptote, just kind of as a reference. And then this is 1. It's not like a 4 or 5 or something, so that means there is no stretch or shrink on it. And we'll only see stretches this quarter for these. So I'm going to have a point there, and I'm going to have a point there. And then our horizontal asymptote hasn't changed because we haven't moved up or down, so it's still the x-axis. So we'll draw that. And then you don't want to draw this going past the asymptote because it doesn't do that. So, and then something like that. For this next one, we have 1 over x, but the whole thing has been shifted down 4 units. So the vertical asymptote is still x equals 0. The horizontal asymptote will also shift down 4 units. So now it's going to be down here at 4. No stretch again because that's a 1, and so we would be right there. These are hard to draw with what I'm drawing with, and right there. And again, there's a vertical asymptote here. So for these ones, we have both an up-down shift and a left-right shift. So we have a -3 on the inside, so that means we're going to go 3 to the right. And then we have a +5 on the outside, so that means we're going to go 5 up. And so that would be where I would do that first click on the computer to set these asymptotes. And no stretch again, so it would just be here and here, and then just kind of looking like that. Kind of looking like that. The next one, so that one has a negative in front, so it's going to reflect. So instead of it looking like this, when I reflect it, this part is down. Oops, that didn't come out very good, but hopefully you know what I mean. And this part is now up. So that's the only difference that negative does. So instead of going up and down with my dots, I'm going to go down and up with my dots that direction. So let's see, this one is down 5 and right 3. So right 3 and down 5. So we'll throw a dot there and then get these asymptotes in for reference. And then negative, and so that means it's reflected, so this should be down here, and then this should be up there. So exact same transformations, just a new picture that we're working on it with. Okay, and then these last two have numbers that aren't 1 up there, so that means there's also a stretch going on. So same strategy, we'll get our asymptotes graph first. So -4 means it's going right 4, +1 means it's going up 1. And then it's stretched by a factor of 3. There's no reflection. That one has the reflection. So this is where it would usually be, is kind of over 1, up 1 from that intersection. But now it's going to be 3 times that much, or 3. And so it's also going to be 3 times as much this way. So you can kind of see the symmetry that I'm doing there. Just counting up 3 from the horizontal asymptote and out 3 from the vertical asymptote. And we get that. And then we'll just do the exact same thing on the other side. So 1, 2, 3 would be right there, and 1, 2, 3 would be right there. And on the computer, that's a lot easier, because you just have to get the 1 point, and then it draws the other 3 for you. And let's see, lastly we got, this one is going to be reflected, so I just have to remember to draw it upside down, and it's going to go right 1 and up 5. So right 1 and up 5 puts us there. And across. And then this one, it's going to be backwards, so instead of being up here, it's going to be here and here. Oh, it's not, because it's 4. Scratch that. Orientation is right, but it needs to be stretched by a factor of 4. So instead of being here, it's going to be 1, 2, 3, 4. Instead of being here, it's going to be 1, 2, 3, 4. So again, 4 away from the axis in each direction. And on this side, 1, 2, 3, 4. So there, and the other one is up off the graph, but it would look something like that. So that is the graphing with transformations part. This next bit here, this is a just kind of an overview of the things from the last section that we learned about asymptotes and x and y intercepts. So remember that when we have a rational, zeros from the numerator, that's going to be our x-intercepts. So for instance, the easy one, let's say we had y plus 3, or y equals x plus 3 over x minus 1. So my x-intercept would be at -3 for that. The zeros from the denominator give the vertical asymptotes, so that would be x equals 1. I would have a vertical asymptote there. And then the stretch factor is something that we're going to have to determine. When we have the equation, for this one, we can look at it and it's going to be 1 over 1, so it's 1. If I threw a 2 on there, now it's stretched by a factor of 2, because it would be 2 over 1. So if there does happen to be the same version of horizontal asymptotes, which there will be, that actually gives us our stretch. Otherwise, we have to resort to using a point, which is often the y-intercept. Then we solve for a, just like we did in the polynomial section. What else is there to see here? So in terms of intercepts, if we have an even power of intercepts, like if this is squared, we're going to see a bounce like that. If I have an odd power, so like I had it before, where this is just to the first, we'll see it cross at that particular intercept. So even powers bounce and odd powers cross, just like they did in previous sections for polynomials. And then at the vertical asymptotes, if we just have one factor of this x minus 1 essentially to the first, it's gonna act like 1 over x. One side's gonna go down forever, one side's gonna go up forever. But if I throw a square on that, now it's gonna look like x squared, where they both go off in the same direction. And so what it will look like is what we see right here, where both sides are either going to positive infinity or if there's a negative involved, both sides could be going to negative infinity. So that's kind of the bits and pieces, and now let's put that together and write equations based on some graphs. So we're given this graph, and changed back. We are asked to find the equation of this graph. So with this one, I can see I have a vertical asymptote right there at 2. So we'll do y equals, and this is that same a, it's our stretch factor that we did with parabolas and with polynomials. And I know downstairs I have an x minus 2 to produce that vertical asymptote at x equals 2. There are no x-intercepts, which means there is no x up in the numerator. So this is all it's going to be, and then we just need to find a convenient point. There's one now. To plug in for x and y, and we solve for a. So that y-intercept is when x is 0, y is negative 3. So we'll toss that into the equation and solve. So 3 equals a over, if this is 0, that would be negative 2. Multiply that up, it looks like a equals 6. Sorry, I just noticed an error in my notes. I was just making sure it's my notes and not here. Nope, this is correct. So a equals 6. And so then that means y equals 6 over x minus 2. For this next one, a little bit more going on. So it looks like we have a vertical asymptote at negative 3 and 4, and we have an x-intercept at 2. It's crossing, so that's going to be to the first power. We have a y-intercept there at 1 that we can use. And this asymptote, this side is going to negative infinity, and this side is going to positive infinity. So that means it's going to be to the first. And this one, notice though, is going off in the same direction, so that tells me there's a squared on that one. So let's get all that written up. So we'll use our a as our stretch constant that we're going to look for. Numerator is x-intercepts, and that's right there, so that's going to be x minus 2 is the factor that would give me an intercept at 2. Right here I have a vertical at minus 3, so then that means I have x plus 3. That didn't come out very good. And then that one's to the first, because that side's going to negative infinity, and that side's going to positive. Up here, this one we have a vertical asymptote at 4, so that means I have minus 4. And then the graph is heading off in the same direction, so that means that needs a square. And our last piece of information is right there. We have a y-intercept at 0, 1. So again, now I have a x and a y that I can plug in and use to get a. So y equals 1, that'll be negative 2, and 3 times negative 4 quantity squared would be 16. So that would reduce and become 1/8. So this is going to be, let's put the negative in the denominator. So multiply it up here in a second. 2 over 48 would be a 24 down there. Or you can think this is 1 times a and 8 times 3 when I reduce those. Multiplying that up, and I get negative 24 equals a. So my answer on this would be y equals negative 24 x minus 2 x plus 3 x minus 4 quantity squared. The next one is essentially the same thing. Here we have an x-intercept at 2, and that one is bouncing this time. So let's go ahead and write this down as we talk about it. So that would be a factor of x minus 2, and then it has to be squared because it's coming down and touching and coming back up. vertical at -3, so that means we have an x plus 3. And going opposite direction, so it's to the first. Then we're going to have an x minus 4. And that one's going to be squared because both sides are heading up like 1 over x squared does. And then, let's see. Oh, for this one we're told right here in the directions. Remember, it took me a while to find that. The y-intercept is at 0.4. So we'll have 0.4 equals a. And then -2 times -2 is going to make a 4 right there. And then 3 times -4 times -4 will make 16. And then we reduce that a little bit. 4 goes into 16 4 times, so this is a over 12. And then multiplying that 12 up times the 0.4, and we get 4.8 for a. And so I won't rewrite it again, but that just means that this right here would be